In algebra, we often need to find the region where multiple conditions are met simultaneously. When these conditions involve powers higher than 1, we enter the world of nonlinear inequalities. Today, we will learn how to visualize and solve these systems using coordinate graphing. Nonlinear inequalities are essential for modeling real-world constraints, such as satellite coverage zones, structural stress limits, or economic feasibility regions. Mastering the graphing method allows us to see exactly where solutions exist within these complex boundaries. The first step is identifying the boundary. If the inequality includes equal to, use a solid line. If it is strictly greater than or less than, use a dashed line. This boundary divides the coordinate plane into distinct potential solution regions. To represent the inequality, we shade the region that satisfies the condition. For functions solved for y, greater than a typically means shading above the curve, while the less than a means shading below. This visualizes all possible x, y pairs that make the statement true. When in doubt, use a test point not on the boundary, like the origin. Plug the coordinates into the inequality. If the resulting statement is true, shade the region containing that point. If false, shade the opposite side of the boundary. A system consists of two or more inequalities. The solution to the system is the intersection, or the overlap, of all individual shaded regions. Let's look at a system involving a quadratic parabola and a circular boundary. First, we graph the parabola y equals x squared minus 4. Because the inequality is greater than or equal to, we draw a solid line. Since y is greater than the expression, we shade the interior area above the vertex. The solution to the system is the region where both shaded areas overlap. This intersection represents all coordinate points that satisfy both the parabolic constraint and the circular constraint simultaneously. Any point in this double-shaded zone is a valid solution. By shading above the first and below the second, we find a confined, lens-shaped region. This illustrates how nonlinear systems can create bounded areas of solutions, which is a common requirement in manufacturing and resource allocation problems. To be precise, we find where the boundaries intersect by setting the equations equal to each other. Solving this reveals the exact coordinates where the solution region begins and ends, providing mathematical rigor to our visual graph. It is possible for a system to have no solution. If the shaded regions do not overlap at any point, the intersection is the empty set. This means no single point can satisfy all the conditions of the system at once. Common mistakes include using the wrong line type or shading the incorrect region. Always double-check the inequality symbol and use a test point like 0, 0 or 1, 1 to verify your shaded area before finalizing your graph. To summarize, start by graphing the boundary equations. Determine if the line should be solid or dashed. Shade the appropriate region for each inequality, and finally, highlight the area where all shaded regions intersect to find your final solution. Let's do a quick check. Given the system y is greater than or equal to x squared and y is less than or equal to 4, is the point 0, 2 a solution? Plugging it in, 2 is greater than 0 and 2 is less than 4. Yes, it is. Graphing nonlinear inequalities transforms abstract algebra into a clear visual map. By following these steps, you can solve even the most complex systems with confidence. Thank you for watching this lesson, generated by VisionSolve AI.